basic knowledge is required in statistical mechanics. The first thing which you should note that there are many questions in gate and net which requires the calculation of the number of microstates. So number one is there will be 2 or 3 problems in every year in gate and net which makes use of the calculation of the number of microstates for any particle species, which may be bosons, fermions, or classical particles. So these types of questions come. Okay. So if in any question nothing is mentioned, like bosons or fermions or anything, nothing is mentioned, you should assume it to be classical particles obeying Maxwell-Boltzmann statistics. Okay. Now, next type of questions. So these are types of questions. So next type of questions come on finding the partition function of a system, mostly in canonical and grand canonical ensembles. But mostly in case canonical comes. And third is finding the average quantity average quantities means this thermodynamic variables, macroscopic variables. For some system. Okay. So I hope you have all done the canonical, microcanonical, canonical, and grand canonical ensembles and the partition functions of those in these 3 ensembles. And you know about the Bose-Einstein and Fermi-Dirac statistics and the Maxwell-Boltzmann statistics. Still, before that, I will just want to give a gist of this statistics and their properties. So, are you all familiar with all these concepts? You can answer me.
Yes, sir.
Okay. So, in your syllabus, there is given only 3 Bose and Fermi gases. Free gas, if nothing else is given, you should take it as free, means these bosons or fermions are having only kinetic energies. They are not interacting with each other through any potential. Okay. So that is there in the syllabus. Now, the first and foremost thing, whenever you get a statistical problem, the first and foremost thing is to find the partition function of the system. The partition function of the system, once you get it correctly, it will give you the partition function will give you the all the thermodynamic parameters, the thermodynamic variables of the system which you want, the average thermodynamic variables. But finding the partition function is the main challenge. And if some in calculation of the number of microstates, mostly you can get the entropy, that is S equals to KB ln omega, where omega is the number of microstates. Mostly they will ask about S, or in how many ways these number of particles can be put in these number of energy levels and all this. So basically you have to know two things. One is the counting problems or the problems of combinatorics, and some mathematical problems to find the partition function of the system. Okay. So let's take one example, the simplest example that came in GATE 2040. So as I go on with these examples, I will give you the theory behind it just to get refreshed. So here it said that consider a system of three fermions, three fermions, which can occupy any of the four available energy states with equal probability. Probability. What is the entropy of the system? The entropy of the system is. Now, from the theory, we know that there are three types of particles. One are classical particles, one are bosons, which do not obey Pauli's exclusion principle, and which are fermions, which obey Pauli's exclusion principle. What is Pauli's exclusion principle? That no two fermions can occupy the same quantum state. So bosons, in the case of bosons, we have any number of particles, bosons can occupy the same quantum state. So bosons, they are indistinguishable. Indistinguishable means that, let's say, photon, you cannot distinguish between this photon and that photon. So all photons are same. They are indistinguishable particles. Do not obey Pauli's exclusion principle. Then fermions are another class of particles. They are also indistinguishable, but they obey Pauli's exclusion principle. The classical particles, which is called Maxwell-Boltzmann classical particles, they are distinguishable. Distinguishable means they can be distinguished from one another. I will come what do you mean by distinguishable. And there is no concept of Pauli's exclusion principle because this is a classical system. Now, in what ways these Maxwell-Boltzmann particles can be distinguished? Now, let's say there are GI number of states, all having the same energy. That means GI degeneracy is there. So if they are having same energy, so the probability of occupancy is the same for all. Then how will you distribute Ni number of particles? This Ni number of particles may be Maxwell-Boltzmann particles, bosons or fermions into these GI states, GI number of levels, conforming to these conditions. One is classical particles, which are distinguishable. One are bosons, which are indistinguishable but do not obey Pauli's exclusion principle. And one are fermions, which are indistinguishable but obey Pauli's exclusion principle. Now, first, let us come with Maxwell-Boltzmann. That is classical particles. Classical particles are distinguishable by the fact that the particles which are having different energies, they are looked upon as differently. That means if a particle is having energy of, say, 1 joule and a particle which is having energy of 2 joule, they are different. But in quantum physics, quantum statistics, when we say bosons or fermions, if a particle is having 1 joule energy, if a boson or an electron is having 1 joule energy, and another electron is having 2 joule energy, those electrons are not different. They are the same, but one is having 1 joule and one is having 2 joules. So in Maxwell-Boltzmann case, if you swap, let's say this is, okay, let's say this is 2 joules, this state, and this is 1 joule state. So in Maxwell-Boltzmann, these two are distinguishable. That means if this particle is red and this particle is blue, so I can say that the particle which is having 1 joule is red and the particle which is having 2 joules energy, which is in the state 2 joule, is blue. So if I swap these two, then I can say that 1 joule particle has gone to 2 joule state and the 2 joule particle has gone to 1 joule state. That is a different microstate. This is MB, Maxwell-Boltzmann. For Bose-Einstein and Fermi-Dirac, it's not the case. This is 2 joules. This is 1 joule. If a boson is here with an energy 1 joule and another boson is here with an energy 2 joules, then both the bosons or fermions are identical, indistinguishable. Now, if I swap these two, there is no change of microstate. So for this is Bose-Einstein Fermi-Dirac. So for quantum statistics, it doesn't matter that which particle is in which energy state. Okay, it only matters how many particles are there in one energy state. Okay, how many particles are there? That is the number of particles in per energy state, which we call the occupation number. But for Maxwell-Boltzmann, this number actually is different because I can distinguish them. So if GI number of energy level, states are there with all with energy level E, that means all have same energy. GI is the degeneracy. And I want to put Ni number of particles in GI states. For Maxwell-Boltzmann case, how can we distribute? The way I can distribute this is that the first particle, let's take, I have first particle. So the first particle can be put in GI states in GI ways. The second particle can be put in GI states in also GI ways. The third particle will put GI states in also GI ways. So you have for first particle in one way, there are GI times GI number of ways the second particle can go to. You can think this as of a combinatorics problem. So for the second particle in one state, you have GI number of ways the third particle can go. So the number of ways in which Ni number of Maxwell-Boltzmann or classical particles can be put in GI states is, that is, we call it W. Ni is GI to the power Ni, but all these Ni particles are in the same energy state E. So all these Ni particles are actually identical because we distribute states in partition functions by the energy states. If energy states have GI degeneracies, then I can put this Ni number of particles in GI to the power Ni ways, but actually these Ni number of particles are identical. So you have to divide by Ni factorial. Okay? If this is Maxwell-Boltzmann, if this is Bose-Einstein, then things will be a little different. In Bose-Einstein case, all the number of particles are identical. But any number of state, one state can take any number of particles. One state can take one particle, one state can take two particles, one state can take zero particle, one state can take up to Ni particles. So how many ways can I distribute Ni number of bosons in this GI number of states is the number of ways. This is a little bit tricky. This is, you can just look here. So GI number of energy levels, I put GI number of boxes. So these are GI. This is first box. This is second box, third box, to GI number of boxes. Now, the first box can take any number of particles. Now concentrate on how many ways these walls. See, now if I give number of bosons in a particular box, take for example that the wall right hand side to these balls is the owner of these bosons. So there are GI minus 1 number of owners, walls. So there are GI minus 1 walls. So the first wall can take Ni particles. The second wall can also take Ni particles. So the first one corresponding to one choice. So there can be Ni number of bosons here. Now, for it can take one boson. Here it can take Ni minus 1 boson. The rest may be 0. So it can take 2 bosons. There can be, here they can take 2 bosons. Here it is Ni minus 4 bosons. The rest can be 0. So you can try to shift these walls, GI minus 1 walls, to accommodate the number of bosons inside. So it is the same as in how many ways these GI minus 1 walls get these Ni number of bosons. Or so basically there is no restriction on the state, on any state, on the number of bosons. So here it is Ni plus Gi minus 1 C Gi minus 1, which is equal to Ni plus Gi minus 1 C Ni. This is the number. So total number of elements of the boxes plus the balls is the walls and the balls are Ni plus Gi minus 1. So how many of these total elements get distributed among Gi minus 1 walls is the same as how many balls will get distributed into Ni plus Gi minus 1 elements. The other one is WFD, Ni. The Fermi-Dirac distribution says all the Ni particles or fermions are indistinguishable, but one state can only get 0 or 1 fermion. Otherwise, it's not allowed because of the Pauli's exclusion principle. This is much more straightforward, which is maximum number of particles one state can get is 1. So obviously, Ni must be less than Gi. Otherwise, the rest of the particles cannot go in where they can go. So it is as if Gi number of states are being distributed among Ni number of particles. So it is GiCNi. So coming back to the question of this gate, 3 fermions can occupy any of the 4 available energy states with equal probability. So the number of ways in which 3 fermions can occupy 4 available states which are of equal probability is 4C3 ways. So this is equal to 4 ways. This is the number of microstates. So S, that is entropy, is Kb ln4. That is 2 Kb ln2. So this is B. Answer is B. Okay. So if the question was asked 3 bosons, then what will be the answer? 3 bosons which can occupy any of the 4 available energy states with equal probability. So then, if bosons, in case of bosons, what will be the number of ways, the number of microstates? Omega. Can you tell me, anyone? So if you just substitute this. So this is 3 plus 4 minus 1 C3. So this is 6 factorial by 3 factorial, 3 factorial. 6 factorial by 3 factorial into 3 factorial. So this is 4 into 5 into 6 by 1 into 2 into 3. So this is 20 ways. So 20 ways. And if it is Maxwell-Boltzmann classical particles, then omega is 4 cube by 3 factorial. This much number of ways. And accordingly, you can calculate entropy, anything. So these type of problems come. This is one part, that how many number of ways, n number of these particles can be put in this much number of states with equal probability. Obviously, this should be the most important thing, with equal probability. If it is energy state, energy states are not in equal probability, but with a probability e to the power minus Ci by kVt. That I will come. So if you have doubt, you can stop me. Okay, if you have any doubts, because I may not see anyone who is raising the hand. So you can ask. I think I have opened the this mic. Now, just to mention about some formulae. Canonical partition function Z N V T in summation form is summation I over all energy states. If you have degeneracy Gi, so it is Gi e to the power minus beta ei over all energy states. Z N V T. Okay. So most of the problems in statistical physics, I mean real problems, they are not in this form, because there are so many particles that we can substitute this summation by integration. And you should note that this integration we will find out using what is called density of states. Are you all familiar with this term? Density of states.
Yes, sir.
Can you tell me what is that? What is density of states?
Number of states in a given energy.
Do you know about phase space, volume, and differential phase space volume, measure of phase space? What is phase space and phase space volume? Okay.
So these are
Huh?
this is of momentum and number of particles. It is something like that.
Okay. So when we write density of states in the integral, what does it mean? What is the meaning of this density of states in the integral which we use? See, when I'm writing the partition function z as summation, this gi is the degeneracy of energy state ei, but there is no density of states. We have to do it in integral form. We have to do it in integral form. So when we do it in its integral form, then we become something we come that is GDE or GPDP, which we call as the density of states. Have you come across that?
Sir, is it something like continuous energy distributions?
Yes, who is speaking? Can you just tell your name,
Sir,
please?
Ashwin.
Ashwin. Yeah. Tell me.
Sir, excuse me.
I'm not, you are not audible properly, I think.
Sir, is density of states is something like continuous energy distribution, sir.
Yeah, because there
Continuous
are so many
degeneration.
number of particles that we, instead of summation, we use integration. Very good. But it's the volume, since we are using a continuous set of momenta or energy values, we used to say that what is the phase space volume in the range, some range in the momentum range from P to P plus dP, or energy range from E to E plus D. That is the number of states in volume V. The volume V means, if you can also say, if the actually the energy which is a function of P only, because we are using free gases, we can also say that what is the number of states lying in volume V in momentum range or energy range P and P to P plus D, dP, or E to E plus dE.
The density of
So
states multiplied by volume
yes,
or something. So
yes,
the answer would be the density of states multiplied by dV or dE dP something.
GE, or GPDP. Yeah, I'll come. So let's take one more example of this. Now, please remember, if in the question it is not said that whether it is a fermion or a boson or anything, just a gas of particles or anything, you assume that it is classical, Maxwell-Boltzmann. Very important.
We will learn about the diode. And these
Ah,
are the following topics that
yes.
we will cover in the series of videos. And in this particular video, we will learn that what is diode and how the VI characteristics.
What is happening?
So someone has opened their microphones.
Oh, some. Okay. So let's take the CSIR net 2011 question. Set B in this problem is it visible? The slide is visible to everyone. I wrote this canonical partition function.
Yes, sir.
Yes, sir.
I think okay. Anyways, so this is CSIR net. This is 2011. So a gas of n non-interacting particles is in thermal equilibrium at temperature T. So gas of n non-interacting particles is in thermal equilibrium at temperature T. Each particle can be in any of the possible non-degenerate states of energy 0 to E4E. So calculate average energy per particle considering this quantity beta epsilon very less than 1. So now how do you calculate average energy? So the average energy is E average is summation over EI e to the power minus beta EI by Z. This is the average energy for n particles, that is for the gas. Energy of n particles, that is of the gas. So if you want to calculate average energy for one particle, E1, average energy per particle, it is written per particle, then it is sufficient to find out the partition function of one particle. So this is summation EI e to the power minus beta EI by Z1, where Z1 is Z1 phi T. This is the partition function, canonical partition function for one particle. Since there are three states, energy states, I need not do integration. I have to do summation. So now, what is Z1 VT? So this is summation e to the power minus beta ei. So this is summation I. So one state is 0. So I should trace some 1 minus plus e to the power minus 2 beta epsilon plus e to the power minus 4 beta epsilon. This is the partition function for one particle. Okay. The summation I e to the power minus beta ei, all the available states. So this gas contains 3 available states, energy states, of all are non-degenerate. If some state was degenerate, then I would have multiplied that by the degeneracy factor, G. Okay. So now what is E? E1 then 2E e to the power minus 2 beta E plus 4E e to the power minus 4 beta E by Z. Z1 rather. Z1. So this you just write 2E e to the power minus 2 beta E plus 4E e to the power minus 4 beta E by 1 plus e to the power minus 2 beta E minus 4 beta E. Now expand it when beta E is very, very less than 1. So you just, this is approximately equal to 2E into 1 minus 2 beta E plus 4E into 1 minus 4 beta E by 1 plus 1 minus 2 beta E plus 1 minus 4 beta E. So here, by considering the options, you can just neglect this beta E terms. Okay. So this is 60 by 3. This is 2E. Okay. This is the answers. So this is a very simple problem, considering partition function of a system with only 3 states. Now we come to some complicated things. So any doubts? Anyone having any doubt?
No, sir.
No, sir.
Okay. So please remember that the partition function, now let us do the canonical partition function in realistic case. You should remember this, that the canonical partition function Z NVT in the continuous case, you have to use this integral form. So how do you use the integral form? You have to use this integral form by this formula. Let's take, this is the Maxwell-Boltzmann, simplest case. Maxwell-Boltzmann gas. So you have to do this, that integral from 0 to infinity e to the power minus beta e to the power minus beta e into g. It's better. Okay, fine. I write it in this e only. de. Okay. So now, actually, this GEDE consists of the phase space volume element and the the momentum space or energy space volume element and the position space volume element. So in general, if your energy doesn't contain position, energy is the Hamiltonian of a single particle. It may contain x, p, or anything. For a free gas, energy is a function of momentum only. It doesn't contain position. So you can, so here what happens is this d3x is there. So d3x is the volume V into d3p. So your measure will be d3x into d3p. But when you use quantum, this phase space volume, dx dp, the elemental phase space volume dx dp, this will be divided by this elemental phase space volume h. Because due to uncertainty principle, the elemental phase space volume is given by h dx dp. So d3x d3p is dx dy dz, dpx dpy dpz, and every pair will contain an h term. So you have to divide it by h cube. Okay. So you have to divide by h cube. Now, d3x is basically v. You can take it out of the integral because if you consider free gas, all other functions does not depend on x. So you can take it out of the integral and you can take v by h cube. So v by h cube integral in 0 to infinity e to the power minus beta e g d. Now it's easier since e is a function of p. Basically, if it is non-relativistic, p square by 2m, e is a function of p, then it's better to use gpdp instead of gd. So gpdp is basically what is the phase space volume element, phase space volume between the spheres in the momentum space of radius p and p plus dp. So you have this momentum space and you have a sphere of radius p, another sphere concentric, you have radius p plus dp. This is p plus dp. What is the number of states lying in this annular region between these two concentric spheres? Is just 4 pi p square dp. It's this surface area of the lower sphere into into the thickness. Okay. So this integral comes out to be 4 pi v by h cube integral 0 to infinity e to the power minus beta p square by 2m into p square dp. So this integral can be done, okay, using gamma function. And please remember that this is always equal to v by lambda q. Actually, this is, I am doing it for one particle. Sorry, I did it for n particle. For one particle, it is v by lambda cube. What is this lambda? Can anybody tell me? This you should always remember, that the partition function of one particle in a gas with a huge number of energy states, continuum energy states, is v by lambda. Can anybody tell me what is this lambda?
Compton wavelength.
This is called thermal de Broglie wavelength. Lambda. So the partition function of a classical gas of one particle in a classical gas is given by V by lambda cube, where lambda is the thermal de Broglie wavelength. Okay. Now, if the particles in the gas are not identical, that is, they're different from each other, then the partition function of this whole gas is just Z1 Vt to the power n. If they are identical, then n factorial. Please note, this is very, very important. I mean, then you don't have to work out. So this is for a normal gas containing Maxwell-Boltzmann particles, classical particles, which are the same, say any gas at very high temperatures. So having n number of particles in a volume V in equilibrium at temperature T, so ZnVT is V to the power n by lambda to the power 3n into n factorial. Please remember this. This is very important. So all of your classical thermodynamic relations, the pressure, the other things, free energy, Helmholtz free energy, pressure, and everything will come from this partition function. Now, what is the relation between Helmholtz free energy and partition function? What is the relation between F, your thermodynamic parameter, Helmholtz free energy, and the partition function? So F is equal to minus kBT ln Z. Okay. Can you understand this? This is the very the old relation. F is equal to minus kBT ln Z. And F is equal to U minus TS. This is from the first law, U minus U plus PV. So this is PV is equal to kBT ln Z. Always remember that in the grand canonical, or anything, PV is always equal to kBT ln Z. So this is the relation between the partition function and the thermodynamic parameters. Once you get free energy or PV, you can get all other thermodynamic parameters from this relation by using derivatives. Okay? Any doubts?
Sir,
Yes.
sir, can you please
Can
explain
you
once
please
again?
tell your name?
Sir, Akhil Kumar.
Oh, okay. Fine.
Sir, sir,
Yeah.
this formula in the box, the right hand side, z equals v to the power n upon lambda to the power 3n and factorial. Sir,
Yes.
what are the conditions for this formula?
The conditions of the formula, this one, that is v to the power n by lambda to the power 3 into n factorial is if all the particles in this gas are identical. That is, let's say you have helium atom, helium gas, or hydrogen gas in the sun. It's huge temperature. So hydrogen, all there are hydrogen atoms. All hydrogen atoms are identical. Then what is the partition function of this gas? Then partition function of this gas is given by this. If n particles are not identical, all are different, then the partition function will be given as only z1 vt to the power n, that is v to the power n by lambda to the power 3n. You do not divide by n factorial. Okay. So can anybody tell
Okay,
me why do we divide by n factorial? In case if it is identical.
Gibbs paradox.
No. Gibbs paradox, you divide it by n factorial, but what is the physical meaning of it? Yeah, you have come to Gibbs
To avoid
paradox.
double counting something and also.
The thing is, this box contains same number of particles. Let's say these are particles, identical particles. These identical particles can be in every point in the phase space volume. Okay, but swapping of any two particles will not create a new microstate. Let's say this is the box with volume V. So if I swap this particle with this particle and this particle with this particle, does it make any difference? So that doesn't make any difference. So it's like I have this number of balls when you did permutation and combination in your class 11, 12. So this number of balls are there, red balls. If I swap this with this and this with this, so this will not make a new arrangement. The arrangement will be the same. So if you have n number of red balls, m number of blue balls, p number of green balls, then in how many ways can you get different type of arrangements? You can get different type of arrangements in n plus m plus p whole factorial by n factorial m factorial into p factorial ways. Because these n red balls are identical, p green balls are identical, and m blue balls are identical. So that is why this Gibbs, you can say right, it's Gibbs correction factor, n factorial, this comes with a correct enumeration of the number of microstates. Good. Now, we will start with the quantum statistics, that is the Bose-Einstein and Fermi-Dirac. But the problem with Bose-Einstein and Fermi-Dirac statistics is that the canonical version partition function you can find when the number of states are, say, limited, energy states are discrete, say 5 states, 7 states, there are problems like that. But if you have a continuum number of states, then it is tractable to find the grand canonical partition function of the system. So in the canonical ensemble, we had the ensembles were sharing energy through sharing heat through the internal energy alone. But in the grand canonical partition function, grand canonical system ensemble, not only the system can exchange energy, but also can exchange number of particles. So there is another term coming in this grand canonical partition function, which is known as the chemical potential, mu. So here, if the partition function for a canonical partition function for this Maxwell-Boltzmann gas, or not Maxwell-Boltzmann gas, let's say anything, is ZnVT. Then the grand canonical partition function Q, this is called the grand canonical partition function, is given by summation n is equal to 0 to infinity. N is the number of particles. So number of particles can vary from 0 to infinity. Z to the power n, Z nVT, where this Z is known as the fugacity. This is e to the power mu by kBT, where mu is known as the chemical potential of the system. Okay, so Z is known as the fugacity, which is a e to the power mu by kBT. So this is the definition of the grand canonical partition function. So grand canonical partition function is the weighted sum of the canonical partition function with the weight factor as Z to the power n. Okay, this is Z to the power n, Z nVT. And for Maxwell-Boltzmann case, this is just P identical particles. This is very easily done. This is X of ZV by lambda cube. Please remember this. So these formula you should remember to save time. So the Q, the grand canonical partition function for a Maxwell-Boltzmann gas, this is NV gas with identical particles. Is this the number? So you can get all these things like the number density, sorry, the average number of particles n bar or n average is Z del ln Q del Z. The internal energy as minus del ln q del beta. All these are formulae you should learn. Z del ln q del z minus del ln q del beta. Okay, and again PV is always kBT ln q. So whether it is canonical or grand canonical, PV is always equal to kBT ln q. Okay. For Bose gas, Q is pi epsilon for all energy states 1 by 1 minus Z e to the power beta epsilon. Okay. So this is for a free Bose gas. The grand partition function is sum pi. Pi means sum. 1 by 1 minus Z e to the power beta epsilon 0 into 1 by 1 minus Z e to the power beta epsilon 1 into 1 by 1 minus Z e to the power beta epsilon 2. Like that for all the energy states. You have to multiply this thing. And for Fermi gas, Q is equal to pi epsilon 1 plus Z e to the power beta epsilon. Yeah. Yes. Now, there is something known as the distribution function. Bose-Einstein and Fermi-Dirac distribution function. Can you tell me what is the Bose-Einstein distribution function? F. Can anyone tell me? FBE equals to what is the distribution function for Bose-Einstein statistics?
One by two to the power minus one.
You should remember this also. The distribution functions for, sorry, I think this won't come. It will be minus. Minus. Z e to the power minus beta epsilon. So the distribution function is known as the mean occupation number. The mean occupation number is known as distribution function. This you can get it from the partition function Q. The grand partition function is minus 1 by beta del ln Q del E. So I'm writing it this F as a function of T. So Z T. So for Bose-Einstein case, this will be 1 by Z inverse e to the power beta E minus 1. So this is 1 by e to the power beta into E minus mu minus 1 and FFD equals to 1 by Z inverse e to the power beta e plus 1. This is 1 by e to the power beta into e minus mu plus 1. Okay. And at very, very high temperatures, Bose-Einstein and Fermi-Dirac case goes to Maxwell-Boltzmann case, where FD, sorry, MB equals to approximately equal to Z e to the power minus beta epsilon. Minus mu. Now, the thermodynamic variables like the pressure, energy density, energy, number density, all can be derived either from the partition function or from the distribution function, any one. So if you have photon gas, phonon gas, specific heat, then what? Free energy, specific heat at constant volume, specific heat at constant pressure, whatever it is, you will all get from these partition function or distribution function. So let us, I think, what is the time? 12:52. Okay. Let us do one problem. A very good problem, but it came lot of times in CSIR UGC net gate. This came in again. I think I'll do a generalized version. Let's say you have, so let's say everybody knows that these photons and phonons are all obeying Bose-Einstein statistics. So you know about this black body radiation and Stefan's law. Everybody is familiar with the black body radiation. Are you familiar, all of you? Stefan's law of this thing, Rayleigh-Jean's law, Wien's law, and this Planck's law of black body radiation. Have you done? Yes or no? Huh?
Yes, sir.
Whatever.
Yes, sir, but a little bit forgotten.
Obviously we'll forget because this subject is not to be remembered. So in the case of photons and phonons, Z is 1. It's because these photons are first of all massless particles. So this I should make it, clear that let's say massless particles. This is a real trick. You can do it. Massless particles, maybe bosons or fermions. Whatever. If it is bosons, then it may be photon. Sometimes people use neutrinos as also massless particle, but neutrinos are fermions. So E is equal to PC from relativity. Massless particles have energy dispersion relation. E is equal to PC, linear dispersion. So if you want to calculate the average energy of a gas of massless particles, massless bosons or massless fermions, you have to use like this. So U is, so first you have to find like this. So U is equal to V by H cube integral 0 to infinity EP. E is the function of P. This is EP. You have to substitute here. FP GP TP, where your GP dP is 4 pi p squared dP. And FP is your distribution function, whether it is a Bose-Einstein or Fermi-Dirac distribution function. You can do this way, this average U minus del ln Q del beta also. You will see that both these forms will give you the same. So now you will see here how tricky this is. I mean, but it is very easy. So this is V by H cube integral 0 to infinity Pc into 1 by, now Z is 1, zero chemical potential, with zero chemical potential. So Z is 1, mu is equal to 0. So Pc, so Z inverse, so you remove this. So e to the power 8, e to the power beta Pc plus minus 1 into 4 pi p square dp. Okay. Did you get it? So now, in general, what we do is, in case of this massless particles, we don't use this P, but we use omega. So E is equal to H cross omega, just as you did in solid state. P is equal to H cross K, or in quantum mechanics, something like that. So we gave, instead of GP dP, we use G omega d omega. Okay. So if you use, so basically P is equal to H cross omega by C, because E is equal to PC and PC is H cross omega. P is equal to H cross omega by C. This is known as the dispersion relation. So therefore GP dP equals to 4 pi p squared dP is 4 pi into H cross square omega square by C square d of H cross omega by C. Okay. So this is some sort of 4 pi H cross cube by C cube omega square d omega. Okay. Did you get it? So now you substitute here H cube integral 0 to infinity H cross omega by e to the power beta H cross omega plus minus 1 into 4 pi this thing H cross cube by C cube omega square d omega. Okay. Now, whatever it is, this integral is something, some constant into integral 0 to infinity omega cube d omega by e to the power beta h plus omega plus minus 1. So this is C integral 0 to infinity beta h cross omega whole cube d of beta h cross omega by e to the power beta h cross omega plus minus 1 divided by h cross to the power 4 beta to the power 4, whatever it is. So now see, this integral is of the order of t to the power 4 integral 0 to infinity x cube dx by e to the power x plus minus 1. Now, this is a finite constant number, maybe Riemann's zeta function or Dirichlet's eta function. But whatever it is, doesn't matter. This is a number. So you see that for massless particles, whether it is bosons or fermions, U is directly proportional to T to the power 4. So CV, specific heat, is directly proportional to T cube. So these are some things which are mostly asked. Okay, you do not need to calculate integral or this thing. You just do some order of magnitude, and then you see that T to the power 4 is coming. Okay. So massless bosons or fermions all have T to the power 4 dependence of U. But if you take massless MB particles, Maxwell-Boltzmann particles, then how U vary with T? Can anyone tell me? Have you done this?
Inverse.
Inverse.
Directly proportional.
Directly proportional to T. Now the pressure is given by 1 by 3 U by V. This is also directly proportional to T to the power 4 for massless bosons or fermions. And this is also directly proportional to T for classical particles. I think in one gate or something this question came. I forgot, but this is a very interesting thing.
Sir,
Yes.
sir, do massless MB particles exist in real world?
Classical particles do not exist. All particles are quantum particles, but in limit of high temperatures, we can take them to be classical particles. But there are no classical particles in real world. Either there are bosons or there are fermions. If you strictly want to do using the full statistics, so at high temperatures, your system will not, the behavior of your system will not deviate much from the Maxwell-Boltzmann case. For high temperature and low densities, your calculation will not deviate much from Maxwell-Boltzmann case, but strictly speaking, there is no Maxwell-Boltzmann classical particle. Forget about massless. Particles are not always quantum. Okay, so any other doubts?
Sir,
Yeah.
sir, U
Yes.
is internal energy, no, in this question. In
Internal
this
energy, internal, yeah. Average
Sir,
internal energy.
what quantity is Q in the previous derivation, grand canonical
Q is the
partition?
grand partition function. The Q,
So, is this
yes. Hello? Yeah.
sir? Sir, is this
Yes.
probability of some kind?
Huh?
Sir, this Q variable, what does it represent physically?
This Q, what does partition function represent? Z, say Z. What does that represent?
Sir, can you solve this using like finding Q, or you can find the Q here only, like the calculation from Q?
No,
I just
what
need
does
the,
that represent actually? That is this partition function, this quantity. This quantity, what does that represent? Can you find it out and tell me in the next class? Any one of you?
sir. Hello.
Hello, yeah.
So my question is, sir, can we find Q in this question here?
Yes, you can find.
So from that, sir,
I haven't. So I haven't done this. Okay. I told you that you can find this energy, but there is another way that PV is equal to KBT ln Q. So this thing, ln of Q, if you find this ln, then what will be this thing? So if you do in discrete case, I will just show you. Let's say I think I have to rub this all. Yeah. So PV PV by KBT equals to ln Q. So Q, let's say we take a Bose gas or anything, say, or a Fermi gas. So pi epsilon for all epsilon 1 plus z e to the power minus beta epsilon. So therefore, ln Q equals to ln of pi epsilon 1 plus z e to the power minus beta epsilon equals to summation of ln 1 plus z e to the power minus beta epsilon. So this is PV by KBT. Now you are making a sum again, ln of 1 plus z e to the power minus beta epsilon. If you want to do integration, then because of the closely spaced energy levels, you have PV by KBT is summation of ln into Gp dp into V by h cube. Again, you do the same thing. So this is V by h cube integral 0 to infinity 1 plus z e to the power minus beta p square by 2m into 4 pi p square dp. If you use non-relativistic case. So next class I will come that there is, have you heard of this Bose-Einstein integrals and Fermi-Dirac integrals? This will come, this Bose-Einstein and Fermi-Dirac integrals. And this next day, we'll discuss on this question of Bose-Einstein condensation. This came in huge time in Mech, in d-dimensional space with any dispersion relation. Then you have to use this so-called Bose-Einstein integrals. And Fermi, there are other integrals, Fermi-Dirac integrals for Fermi-Dirac case. Have you done those things? I think you have done.
No.
Huh? You have
Sir,
not done Bose-Einstein integrals? Because this is the free Bose gas. And on top of that, questions will come. Right?
Okay, sir.
So you can go through this Patria's book, Statistical Mechanics, and write the name, Patria and PL, Statistical Mechanics. So this is a very good book. Statistical Mechanics by actually doing this full course and with questions will actually take 1 year. But it is not possible now. You go through this, and there is another good book also, Rife and Huang. These books are also very good. Go through it. Then you can do the questions in part C, because part C questions in net are little bit concept oriented. Like there was a, I think in net June 2015, an ideal Bose gas in d dimensions obeys the dispersion relation epsilon k is equal to a k to the power s. For Bose-Einstein condensation to occur, the occupancy of excited states, this thing should be finite. So what is the condition between the dimensionality and the this energy momentum relation? So there is a restriction on the dimensionality and energy momentum relation on this Bose-Einstein condensation. Bose-Einstein condensation cannot occur arbitrarily. Okay. So these things you should know, because if you don't know the Bose-Einstein integrals and these things, you won't be able to do it. Once you know this, then it will be very straightforward. Like here. So if they say massless bosons or fermions, you should always know that if it is massless with zero chemical potential, it means U is directly proportional to T to the power 4. And CV is, just don't have to worry about anything. Zero chemical potential and massless bosons or fermions, not Maxwell-Boltzmann particles. Okay, now I think I am out of, you are hungry for lunch. So we'll discuss tomorrow. Okay. So any more doubts? I'll just, if you have.
Sir, phonons are bosons, sir.
Yes. Photons.
No, sir. Phonons.
Phonons are also bosons. Yeah.